Okay, the Taylor series question from 2016 BC exam. We have a function f has a Taylor series centered at 1, converges on the interval of convergence. They give you values of f and f prime of 1. And then after the first derivative, you find subsequent derivatives with this formula. And then they ask you for the first 4 non-zero terms for the Taylor series, which we will get by using the formula, the nth derivative at 1 over n factorial times x minus 1 to the n. And the only time you would not use that, two ways you would not use that is if you are altering the series for e to the x sine x or cosine x, something you've memorized, or if maybe they gave you the first 4 series of the function for f, and then they ask you for f prime, in which you just differentiate the ones given. In this case, though, we're going to crank it out with our good old-fashioned formula. I have f and f prime of 1. I am missing f double prime of 1. That should be a 1. F double prime of 1. And I will get that by plugging 2 into this formula. My second derivative, so negative 1 squared is positive. 2 minus 1 is 1 factorial over 2 squared is 4. And so that's going to give me a value of 1/4. F triple prime of 1 is going to be when I plug in 3. So that's going to be negative. 3 minus 1 is 2. Factorial over 2 cubed is 8. And that would reduce to negative 1/4 also. So it's negative 1/4 instead of positive 1/4. So my first 4 terms. And it also asks for the general term, so make sure you put that in there. So f of x, and don't write equals because a Taylor series is an approximation. Although since we're including the general term, I guess we could say equals. Anyway, so it would be f of 1 plus f prime of 1 over 1 factorial times x minus 1 to the first power plus f double prime of 1 over 2 factorial times x minus 1 squared plus f triple prime of 1 over 3 factorial times x minus 1 to the cubed plus, and then for my general term, this right here will be the formula for the nth derivative. And I have gone past the first, so I can go ahead and use that formula. So that's going to be negative 1 to the n times n minus 1 factorial over 2 to the n. But then you're supposed to divide that by n factorial. So I'm going to stick that in the denominator as well. And that would be times x minus 1 to the nth power plus so on and so forth. And I'm looking at this and I noticed that I could reduce n minus 1 factorial over n factorial. And that would reduce, let's see, I have more n's on bottom. So that n minus 1 will cancel all but the n on bottom. That would reduce to 1 over n. And so if I run into a situation later on in the problem that having the simplified version of this would come in handy, I may reduce that. However, I would not have done that on my written work for the AP exam. I'm only pointing that out for y'all in case you were happening, if you happen to notice that. If you are happening. Anyway. Moving on to B, so the Taylor series for f about 1 has a radius of convergence of 2. That is a gift from the gods that they gave you the radius of convergence, because when you are asked for the interval of convergence, your first thought probably is to do the ratio test. However, the ratio test, the whole point of the ratio test is to find the radius. Knowing that the radius of convergence is 2 and that we are centered at 1, I can, instead of doing the radius of convergence, I can just count 2 units to the right. That'll put me at 3, and 2 units to the left will put me at negative 1. And I already have the endpoints of my interval. All we have to do now is test those endpoints to see if this series converges at negative 1 or if it converges at 3. So I'm going to test those. So if x equals negative 1, I would have the series, and now I'm going to my general form here. My phone just heard me say Siri. So I'm going to go to my general form here, and now I may use that 1 over n. So that stuff in the front, so I'm going to clean up my general term. That's negative 1 to the n times x minus 1 to the n all over 2 to the n times n. So I'm going to simplify my series to that now, because now I'm actually going to need to use it. So if x is negative 1, I would have the series negative 1 to the n times -1 minus 1, which is -2 to the n over 2 to the n times n. And I'm going to clean that up. -1 to the n times -2 to the n is 2 to the n. And this is going to clean up nicely. And usually it does. Usually these things will clean up to a p-series. When you test the endpoints, my 2 to the n's cancel and we are left with 1 over n. That is the harmonic series, which diverges. So this series will diverge on the left endpoint at -1. And then I'm going to test x equals 3. Let's see what happens here. And so -1 to the n times 3 minus 1, which is 2 to the n, over 2 to the n times n. My numerator is -2 to the n over 2 to the n. Oh, wait. Don't do that. Go ahead and cancel the 2 to the n's. How stupid. What was I thinking? Let's get rid of this. Okay, so now I have -1 to the n over n, and that would converge by the alternating series test, or you could say it's the alternating harmonic series, which converges. Okay, so we converge at 3, we diverge at -1, so my interval of convergence is -1 to 3, and make sure your blocks, your bracket around the 3 is obviously a bracket. I very frequently see students whose brackets and parentheses look eerily similar. So if you're one of those students and you have really crap writing, then you could also write this as, whoops, not that. You could also write this as -1 less than x less than equal 3. Maybe a little bit safer for you sloppy writers. Let's see, moving on to C. Okay, so the Taylor series for f at 1 can be used to represent f of 1.2 as an alternating series. Use the first 3 non-zero terms of the alternating series to approximate f of 1.2. So to do that, I'm going to go back to my series that I got. That's not where I wanted to go. I'm going to go back to my series from part A, and I'm going to grab all of those first 4 terms. Let's see how much I can get here without, whoa, that's not what I want. You need to go back where you were. I'm going to see, can I get the first, good, I can. So I'm going to copy that. And this was my answer to part A. And I'm going to use the first 3 terms to approximate f of 1.2. This is going to be super easy because f of 1.2, all you have to do is plug 1.2 into the first 3 terms. So I'm going to stop right here. Hiccups. Okay, so that will give me 1 plus -1/2 over 1 times 1.2 minus 1 to the first plus 1/4 over 2 factorial, which is just 2 times 1.2 minus 1 squared. And there are the first 3 terms. I have just approximated f of 1.2. I don't know what that value is, and I don't care because all I have left to finish this problem is arithmetic, and you don't have to do the arithmetic to simplify your AP exam questions. And let's look at B. Show that the approximation found in part C is within 0.001 of the exact value of f of 1.2. Bring that over here because I have room to do that on this page. Okay, so we're getting into error approximation, and the error approximation methods that are testable on the AP exam are your Lagrange error bound or the alternating series error bound. And because this is an alternating series, we can use the alternating series, which is the easiest of the error approximation methods. And it's also, fortunately, the most accurate. It gives you the smallest window of error. And so because the series alternates, the maximum error is your very first omitted term. So all I'm going to do mathematically, the actual arithmetic, is I'm going to plug 1.2 in for x here, and I'm going to clean up 1.2, clean up that fraction, and hopefully we will get something less than 1 over 1,000. And so let's do that. But first, sometimes they have these little hoops you have to jump through. And in problems like this, you have to establish the criteria to use that alternating series error test. And so I'm going to write out this long, complicated sentence. And I'm actually going to type it because I can type a heck of a lot faster than I can write. And so the Taylor series, I'm going to quit talking because if I talk and type at the same time, I have a hard time. Oh, I'm going to rewrite that. The terms of the Taylor series alternate and decrease to 0. So basically, I'm saying the alternating series terms converge. So the terms of the Taylor series alternate and decrease to 0. Therefore, the max error is less than the first omitted term, which is, and here is where I'll actually pick up, do some of the math stuff. So my first omitted terms, I use the first 3 terms. My first omitted term is going to come from this. And so I'm going to plug 1.2 into that. So I have negative 1/4 over 3 factorial times 1.2 minus 1 cubed. And let's clean that up. So that's 1/4. 3 factorial is 6. And that will be 0.2 cubed. 0.2 is 1/5. So that's going to be 1 over 4 times 6 times 5 cubed. So 4 times 6 is 24. 5 cubed is 125. And is 24 times 125. I need this to ultimately be less than 1 over 1,000. And so if you're not 100% sure, we can just do some old school multiplication. 125 times 24, not 25. And let's see, so that'll be 20, carry my 2, that'd be 10, carry my 1, that'd be 5. 2 times 5 is 10, carry my 1, that'd be 5. 2 times 1 is 2, and you end up with 3,000. So we get 1 over 3,000, which is less than 1 over 1,000. And so there we have shown that the sum of the first 3 terms does approximate the true value of f of 1.2. And they said less than 1/1000th error, but we actually got 3 times better than that. So there you are, 2016, I believe this was number 6.